Hello there, and welcome to our next lecture in our series. This is chapter 7. Part 1 of this lecture is going to be a two-part lecture here. In this first part of this lecture, we will talk about grams to moles. We'll also talk about our friend's Avogadro and his number. I guess there's nothing left to do but say, let us begin. Part 1 of chapter 7. Okay, welcome back here. Chapter 7 up on tap for today. Chapter 7 is quantitative composition of compounds. We're going to talk about some very important units here in this chapter. We're going to talk about our friend the mole, not the furry guy. We're going to talk about also Avogadro's number. And we're going to talk about some important calculations, including some two types of formulas. We're going to talk about empirical formula and also molecular formula, what they are, how to calculate them, and maybe a little bit about why they're sometimes used. So let's get going on this here. So earlier on in an earlier chapter, we talked about atomic mass, and a reminder that the atomic mass is what we do see on the periodic table. So once again, when we do look on the periodic table, for example, something like our friend here, hydrogen, we see this number on the bottom, which is 1.008. We can see it for other elements as well, like carbon is 12.01, that number there on the bottom. And also, would do our friend nitrogen, which is about 1401 as well. So all these numbers on the bottom, as we talked about, I think in that chapter, we were talking about kind of atomic number, mass number, and all that. Remember, that is not the mass number on the bottom. That is the atomic mass. And that is basically the mass of all naturally occurring isotopes of that particular element. Remember, we talked about the calculation to calculate atomic mass. And just a quick review of that. The atomic mass is basically the percentage of that first isotope times the atomic mass of the first isotope. And then we would add that to the percentage of, say, the second isotope that we have, times the atomic mass of the second isotope. And we would basically just continue that pattern. And that's essentially how we get these numbers that we see on the periodic table. Remember that some elements have maybe 1, 2, 3, 4 naturally occurring isotopes. And it is sort of an average value of all those naturally occurring isotopes of how we get that. Isotopes, as we also talked about, I think in that same chapter, is really the same element, but they have different masses. The reason they have different masses is because they have different numbers of neutrons. Remember that it is the protons that is the most important in terms of what element it is. So as long as the protons don't change, they should all be the same element. And that number of protons is I'll write it up here, sort of, is the number that we see typically on top of this symbol there. And that again is our atomic number, which is our number of protons. So just a little review of that. When we do take this number off the periodic table, typically speaking, the bottom number there, the atomic mass, and more so the molar mass that we're going to talk about more in this chapter, we typically take it to 4 significant figures is usually how far we take it. So what does this number mean? This number means, for example, if you had hydrogen here, there is the atomic mass of hydrogen. Would be there's 1.008 AMU in an atom of hydrogen. And remember, the AMU is atomic mass unit, and that is a unit of obviously atomic mass. And that is usually the symbols that most people use. I know in your book, I believe we might even see it a little bit later, they may just use the U to represent atomic mass unit, but a lot of times people will use AMU as it. So that's one type of unit that we could get off the periodic table. Again, you could get that for any element that is present, and it's that number on the bottom represents, again, how many AMU or atomic mass units there are in one atom of that particular element. We want to kind of remind ourselves on this sort of topic here, because we are going to go back to the periodic table here shortly in this chapter and use that number in a more sort of usable unit. that we use, say, in the lab or just in everyday sort of research rather than atomic mass unit. So just to kind of preview it, grams, for example, is a unit that we use a lot, say in the laboratory, and a more sort of useful unit. And we're going to talk about sort of the relationship of atomic mass that we see on the periodic table, and later on molar mass that we will see. So just wanted to review that a little bit. So let's get into molar mass and Avogadro's number. And the first thing we're going to really talk about is the idea of a mole. And as I mentioned before, the mole is really a name that is used in chemistry to represent a certain amount of something. So not the little animal mole, but it is the mole. The mole, by the way, represents a certain amount of something. And for example, in life, we have a lot of things that we have a particular name for that represents a certain amount of something. So for example, if we have a pair, like a pair of shoes, that represents 2 a pair typically. We have a dozen roses, a dozen eggs, like we see up there in the left-hand corner of the screen there. That means that we represents basically 12. A gross of pencils, you may not be familiar with that, but years ago in elementary school and stuff, they used to give you a pencil every month, I think. But they come in a gross, which does represent 144. Also, maybe you've purchased a ream of paper, and typically a ream of paper is 500 sheets of paper. So in life, we have a lot of words that represent a certain amount of whatever you may be talking about. And in chemistry, it is the mole that is that sort of word that represents a certain amount. So 1 mole of anything represents basically the amount of elementary entities like atoms, molecules, or particles as there are in exactly 12 grams of the carbon-12 isotope. So if you remember from our talk in the previous chapter and just a moment ago as well, it was that isotope of carbon that they used basically to figure out the atomic masses of all the other elements. And remember that the carbon-12 isotope has a mass of 12 AMU. So there is a relationship in chemistry, and we do use this word mole to represent something. And a mole, by the way, an abbreviation for a mole is MOL. So they had to abbreviate it somehow, so they cut off the E there. And it's really important that when you see MOL, it is a very common mistake that a lot of people make is when they see MOL, a lot of times people's minds jump all the way to molecules. And that is definitely not the case. So it's really important to keep in mind as we go through this chapter, later chapters as well. When you see MOL, it does represent a mole and not molecules. Oddly enough, in chemistry, if they want to do something with molecules, they will actually write out usually molecules completely. So if you see that MOL, it is the abbreviation for a mole. And again, not molecules, which again is a very common sort of error that people make. So what does a mole equal? A mole equals, as we can see here, 1 mole of anything will equal 6.022. There's the whole number there, or part of the whole number, 0.45 times 10 to the 23. Most people will round it to this version of the number. And when we talk about this number here, this is what is known as Avogadro's number. So Avogadro's number is 6.022 times 10 to the 23, not avocados, but Avogadro's number is the name there. And what I mean about different units is this: if we have 1 mole of anything, that would equal and represent 6.022 times 10 to the 23. So kind of similar to, if I had a pair, that represents 2. Similar that if I had a dozen, it represents 12. When somebody says you have a mole of something, it represents that you have 6.022 times 10 to the 23. Now, the units that go with Avogadro's number, which is this guy here, that's Avogadro's number, can be pretty much anything. So it could be particles, as we see below. It could be atoms, if we're dealing with atoms. It could be molecules, if we're dealing with molecules. It could be pizzas if we're dealing with pizzas. It could be shoes. Maybe you need your shoes to get your pizza. So I would say, although a lot of these might be very common units that we see, I would say probably here in chemistry, these are going to be your two big ones. I know I sort of circled the pizza part as well. Maybe it's lunchtime. But atoms and molecules here are really the two units that we very commonly see with Avogadro's numbers. And we'll see some examples of maybe when we would use atoms versus molecules coming up in terms of the units. So 1 mole of anything basically will equal 6.022 times 10 to the 23. How are we going to basically use this sort of Avogadro's number? Really, you want to think of Avogadro's number as a conversion factor. And Avogadro's number is pretty much your conversion factor to go from moles to atoms. And again, it could also be molecules. Or backwards from atoms to moles. And the way that we use this is, like we talked about with dimensional analysis and conversion factors, is we can really write two conversion factors here. We could write in 1 mole, there is 6.022 times 10 to the 23. And I'll just use atoms as my units here. 23. Or we could really write the conversion factor sort of flipped around, sort of the opposite way. So we could write 6.022 times 10 to the 23 atoms over 1 mole. So this is a conversion factor that we would use to go from, as I mentioned, moles to atoms or molecules, are really backwards. So it's also really important, the idea of using Avogadro's number correctly. So what I say by that is sometimes people will learn this conversion or this number and go, you know what, I'm just going to use it in every calculation I come across. So I'm just going to throw in there Avogadro's number. I'm good to go. And a lot of times you don't need to use Avogadro's number in every calculation. So sometimes people, when they do that, they luck out because they kind of like divide by Avogadro's number at the beginning and then kind of go back and multiply by Avogadro's number. So a lot of times they luck out by using it twice, which oftentimes in a calculation, you don't use the conversion factor twice. But a really good rule to think about as to should I use Avogadro's number in this calculation or not is pretty much the units associated with it. So if you are come across a problem where you're given a number that it's in the units of atoms, molecules, probably somewhere along the way, you need to use Avogadro's number to convert to moles. Alternatively to that, I'll spit that out, right? Alternatively to that, if you are looking to solve a problem for something like atoms or molecules, then also Avogadro's number should be used. If there's really no mention of atoms, molecules, particles, those type of things, you pretty much should leave Avogadro's number on the side there. You shouldn't use it. So again, one of the major issues that sometimes happens with students is they want to use this number pretty much in all calculations. So those are the things you want to think about. Does it mention something about atoms or molecules in this problem? If the answer is yes, then the answer might be Avogadro's number might be needed. Again, if there's really no mention of any of that, probably almost safe to leave Avogadro's number on the side and not include it in the calculation. And again, we're going to do some examples here coming up, which might make that a little bit more clearer. So Avogadro's number, as we talked about in the term mole, is used to represent a certain amount of something. So for example, going back to sort of the periodic table, we could really take anybody from the periodic table, and we'll use hydrogen as the example there. And we got 1.008 and 1 up on top. So we could say in every 1 mole of hydrogen, there would be 6.022 times 10 to the 23 atoms of hydrogen. Here, hydrogen is an element, so we're going to talk about atoms, and that is why we use atoms as our relationship there. We could go to our periodic table and we could look at our nitrogen. And we can say the same thing. 1 mole of nitrogen would equal 6.022 times 10 to the 23 there we go, atoms of nitrogen. Now, just like we did previously for each of these, we could write two conversion factors. Once again, here we could do 1 mole of hydrogen will give me 6.022 times 10 to the 23 atoms of hydrogen, or 6.022 times 10 to the 23 atoms of hydrogen will give me 1 mole basically of hydrogen. So again, we could write two conversion factors like we did or talked about previously. Same thing for this guy. We could write 1 mole nitrogen is over 6.022 times 10 to the 23 atoms of nitrogen, or we could flip it as well and put 6.022 times 10 to the 23 atoms of nitrogen is over 1 mole. Now, in addition, maybe we're not talking about something that is just one element or an atom of an element from the periodic table. Maybe we're talking about something that is more of a compound or a molecule. So, for example, if I had 1 mole of water, how many molecules would that be? So, if you think about our logic here, I got 1 mole of water, that would represent 6.022 times 10 to the 23. These would then be molecules of water. Same thing if I had 1 mole of methane, which is CH4. That would equal 6.022 times 10 to the 23 molecules of methane. So here, a little bit different than what we were just doing up on top. Up on top there, this is basically an element kind of by itself, which is where we will use atoms as the units associated with Avogadro's number. Down here, though, we have molecules, basically. H2O is a molecule, right? It has 2 or more atoms together. CH4 is a molecule that has 2 or more atoms. They're both also compounds, not really necessary here, but the Avogadro's number unit changes to molecules here because here we are talking about molecules rather than over here where we're talking about just the atoms in this case. So that's really important as well, the difference in the units. Even using it as molecules, it works the same way. It is still really just a conversion factor where we can write two conversion factors. So for the water example, we could say in 1 mole of water, we have 6.022 times 10 to the 23. And once again here, molecules of water. R, I'll just write it underneath. We could have 6.022 times 10 to the 23 molecules of water per 1 of water. So these are conversion factors, just like kind of in dimensional analysis, basic conversion type problems. You would pick whatever one would be most appropriate for what you're looking for. So here, if we look at this, we see this is a mole of each of these guys. This is sulfur, iodine, iron, and mercury. If you look at sulfur, for example, on the periodic table, you're going to see 3207. Once again, going about 4 significant figures when we look at that number. And that's where we see basically this number is that many atoms. So how can we use this in a calculation? So once again, if we had, say, our hydrogen, if we had 4.2 atoms of hydrogen, and we wanted to know how many moles that was. The key when we look at this problem, for example, is I see atoms, and that is the key to trigger me to know I need to use Avogadro's number, right? Again, it's those words of I got atoms, I got molecules either given to me or that's what I'm solving for. That automatically tells you Avogadro's number needs to be involved. So we saw earlier that again, 1 mole of hydrogen is equal to 6.022 times 10 to the 23 atoms. That's going to give us our 2 conversion factors as I wrote on the previous page. So I'll rewrite it here. 1 mole of hydrogen is 6.022 times 10 to the 23 atoms. Or we could put Avogadro's number up on top, 6.022 times 10 to the 23 atoms is 1 mole of hydrogen. So how would we set this up? We really would just set this up like a dimensional analysis problem where we use conversion factors. We see the units canceling as we talked about in the previous chapter, we would start with 4.2 atoms of hydrogen. Remember that when we set it up using these conversion factors, using dimensional analysis, which is how you should set up these problems, it is always going to be opposites cancel. So remember that although this guy is not really written as a fraction, we see that the units of atoms are basically up on top, and that's what we want to get rid of. So we want to use a conversion factor here where atoms is in the opposite location, and that's what we see here. We see the atoms are actually on the bottom. So we would set this up like so. And we would do our Avogadro's number there on the bottom. And up on top would be 1 mole of hydrogen. Once again, atoms of hydrogen on top and atoms of hydrogen on the bottom will essentially cancel each other out. A reminder that when we do this type of situation here with dimensional analysis, whatever is on the top, we are multiplying, and then we're coming back and dividing by what's on the bottom. So again, mathematically, that is what we're going to do. I'm going to grab my calculator here and give it a go. We're going to go 4.2. And we're going to actually divide it by Avogadro's number, which is 6.022 to the 23. Also really important in this case is making sure you're still using your exponent button. So it's been a couple of chapters since we maybe talked about that. I'm just going to punch it in or write it up here, how you should punch this into your calculator and make sure you get the right answers. So you want to make sure you're using that exponent button. So you're going to take 4.2. Essentially, we're just times them by 1, so we really don't need to do that. We then would divide it by our bottom number, which again, we need to use our exponent button, so 6.022. Remember, you have either an EE button or an EXP button, or again, you could have one of those, as we talked about, kind of two-tone calculators that has the times 10 and a will type button. Remember, if you have that calculator, you do need to put parentheses around the numbers, as we talked about in that chapter. If you're not sure what I'm talking about, you may want to revisit that chapter there in that lecture. We did some examples how to properly punch it in there. Here, it's actually a positive exponent, so we're just going to hit 23, and then we're going to hit equals. Once again, on your calculator here, you should end up with maybe something like 6.974. Do not forget the back part of it, which is times 10 to the minus 24. And these would be moles of hydrogen. We still want to think about significant figures in this case. And in this case, this would be pretty much in most cases considered an exact number. So you really don't have to worry about the significant figures in that number or that conversion. So here's really the only one that kind of has numbers that we would want to look at. And that has 2 sig figs, which means really we should take this number here. And because this is a 7, it actually will roll up. And we should really probably end up with something like 7.0 times 10 to the minus 24 moles of hydrogen. And there would be. Check. So a couple of things. Avogadro's number is a number. It represents a mole of something, and it really is, for all intents purposes, a conversion factor. And it's a conversion factor that you use again to do those conversions: moles to atoms, atoms back to moles, also molecules if you're dealing with molecules. Another really important sort of conversion factor that we use a lot is what's known as molar mass. And molar mass is a really important conversion. I would say probably definitely in real life, sort of more than Avogadro's number. Molar mass is used a lot in a lot of calculations that you do in chemistry. So, this is definitely the one you want to focus in on. Avogadro's number, also really important to know, but this one is super important. I guess if you put super in front of it, it makes it more important. So super important here. Molar mass actually has 2 units associated with it. It is grams per mole. And that is the units associated with molar mass. It has 2 units. Typically, the number stays with the grams part and is per 1 mole. The molar mass is basically the mass in grams of 1 mole of a substance. So as we saw earlier, where do we find molar mass? This is where that sort of atomic mass comes into play. So essentially speaking, when we go to the periodic table and we look at our friend, say, hydrogen, we pulled this off earlier as 1.008 AMU per atom, and that is what is referred to as the atomic mass. A more usable unit is one that involves grams. So if you know, as you go to the balance or scale and you weigh something out, grams are a very common unit that is used. So we can pull this exact same number out. Once again, typically, as we've been talking about, 4 significant figures is how far you want to take that number. Depending on what periodic table you're looking at, you may have more numbers than 4. So you typically want to round to 4. And we can pull that out for hydrogen as the molar mass is 1.008 grams per mole. So the molar mass of something is always how many grams there is per 1 mole. So that unit on the bottom, which is mole, should always be 1. And as I mentioned before, numbers should always stay with the grams part. So we basically could say that in hydrogen, there's 1.008 grams of hydrogen in every 1 mole of hydrogen. We could do that for anybody else that we see on the periodic table. We got our carbon, 12.01. So we could say for carbon, there are 12.01 grams of carbon in 1 mole of carbon. Just like with Avogadro's number, we really use molar mass as a conversion factor. And it is your conversion factor to go from grams to moles in terms of units and backwards, going from moles to grams. That is probably 99% of the conversions you do. A lot of times it is going from grams to moles is a lot of the first steps that you do in a lot of chemistry calculations. So molar mass is really important. We get it from the actual periodic table, and we could write conversion factors just like we did with our Avogadro's number. We could say there is 1.008 grams per mole of hydrogen, or we could write the conversion factor opposite. A mole of hydrogen up on top is 1.008 grams. So we could use them as conversion factors. We could do problems with them as conversion factors, the same sort of way that we use Avogadro's number. So if you look on the periodic table, numerically equal is the number of AMU per atom, the atomic mass, and the molar mass. So the molar mass and the atomic mass you see on the periodic table is actually numerically going to be the same number, and we'll see a little conversion as to how you get there. Not super important for us in here, but it's numerically equal to each other. So sodium is 22.99 AMU. Its molar mass is 22.99 grams per mole. Atomic mass of copper, 6355. Its molar mass would be 63.55 grams per mole. We also, for example, could, if we needed to, get the molar mass of something that is not just an element by itself. So we could have like our molecule guy. We could take something like water. So how would we get the molar mass of water? Well, we would still go to the periodic table. We would find hydrogen. We would also, in this example here, perhaps want to go find oxygen, which if you did is... So we basically define the molar mass here of water would essentially just add up all the parts. So there are two, that number there, remember, goes to the guy to the left. There are two hydrogens, so each hydrogen is 1.008 grams per mole. And we would then add it to our oxygen, which is 16 grams per mole. So if you have something that's a compound, a molecule, and you need the molar mass of it, you essentially just go to the periodic table and you pretty much add up all the parts. So over here represents our hydrogens, and over here represents our oxygens. And then basically we just, and come down here, add those together, and you should get something like 18.01 grams per mole. And that would be the molar mass. I'm probably writing on myself right there, of water in this case. So molar mass of water there would be 18.01. So what can we do with that number? We could pretty much do the same thing as we did with the other. So we have our 18.01 grams per mole as our molar mass for water. So we could write two conversion factors, 18.01 grams over a mole of water, or a mole of water is 18.01 grams. So just like before, you know, perhaps we have 32.5 grams of water, and we want to know how many moles that is, for example. So the first thing we want to think about is, and is a good idea to think about, is this: should we use Avogadro's number in this calculation? So remember that if we want to use Avogadro's number in this calculation, we have to have words like atoms or molecules, particles, something like that. And that's not mentioned. Also a reminder that when we see this guy here, that is not the abbreviation for molecules, but that is the abbreviation for moles. So that's really, really important to keep that in mind. So it's really just a gram to mole conversion, and that is our molar mass. So our molar mass, once again, is our source to go from grams to moles and backwards. So we'll set this up again, just like a dimensional analysis problem, 32.5 grams of water. Once again, grams of water up on top, which means in order for it to cancel, we do need the same units on the opposite location, which means we do want to use the conversion factor here on the right. And we'll set it up with our dimensional analysis here, putting our grams on the bottom and our moles of water up on top. Once again, the grams on top and the grams of water on the bottom are going to cancel. We're basically going to take 32.5 and divide it by 18.01. And that is going to get us here 1.804553 moles of water. Once again, sort of looking at significant figures, probably not going to look at this number here, as it's more of like an exact number. We are going to look at our original number, which have 3 significant figures. That means we really should end up right about there on that number. That's a 4, which means we could just drop the rest of it and probably should end up with 1.80 moles of water. So once again, molar mass, really important, used a lot in chemistry to do those conversions. And as I mentioned earlier, pretty much a beginning step of a number of calculations is take the grams and convert them to moles. So you almost can't go wrong in a lot of calculations in chemistry. If you're like, where should I start? I'm not really sure, but I have grams. probably in most cases, converting it to moles is a good first step. It's probably something that you do need to do in a lot of chemistry type calculations. I won't say everyone, but if you ever find yourself like, I got grams, what should I do with it? Maybe convert it to moles is probably a good idea. Again, not 100% of the time, but a lot of times that is a good step. So just the relationship between AMU and grams, we're going to kind of look at here. I'm going to get rid of some of this on here. So, for example, we look at a mass of a single carbon 12 atom. We see that it has a mass of 12 grams. It is 1 mole of carbon 12. We can use our conversion and our Avogadro's number here. Again, the key here is we have atom mentioned. Using those relationships, we get basically that 1 carbon 12 atom has a mass of 1.993 times 10 to the minus 23. This gives us sort of our relationship between AMU and grams. And we see that doing the calculation here, basically 1 AMU, atomic mass unit. And again, in your book, I think they just use a U to represent that, equals 1.661 times 10 to the minus 24. If you want to know how many AMU that is in a gram, you basically divide 1.66 times 10 to the minus 24 to both sides. And that gives you that 1 gram is equal to 6.022 times 10 to the 23 AMU, pretty much Avogadro's number. So numerically speaking, the atomic mass that you see on the periodic table, which is that bottom number underneath the symbol, is numerically equal to the molar mass that we get when we convert it to a more usable unit like grams per mole for our purposes. So most of the time, people will just kind of sometimes call that number on the bottom there molar mass because that's oftentimes how we use it. But again, molar mass, atomic mass, they're numerically equal. They do have different units, but most of the time when you go to the periodic table, that is what you're going to kind of pull it off and use it as the molar mass, which is grams per mole. And once again, 4 significant figures is the commonly used sort of rule that people follow in terms of how many numbers they should use. So Avogadro's number and also molar mass can be used really as conversion factors. And we can get the mass of atoms and moles of atoms using Avogadro's number. I can also calculate the mass of a single atom. Once again, the key thing that we talked about, Avogadro's number should only be used when we have something to do with atoms or molecules. Again, do not use it in all situations. Here's some of the relationships. And again, for atomic mass unit, as I mentioned earlier, I think in your book, this is what they use for AMU as the symbol. A lot of people use AMU, but U is apparently used here in your book, grams and Avogadro's number. So what is the relationship between Avogadro's number, molar mass, grams, and all that? As you can see in this sort of picture from your book, if we took something, say like our carbon there, in 1 mole carbon, there is 12.01 grams of carbon. But we also know that if I have 1 mole carbon, that also equals 6.022 times 10 to the 23 atoms of carbon. So that is the relationship between those guys. And that means that if you wanted to go from grams all the way, say, to atoms, you need to make a stop in the middle at moles. And kind of 2 conversions, going from grams to moles, that's going to be your molar mass from the periodic table that you're going to use to do that. And going from moles to atoms, that is going to be your Avogadro's number. So your 6.022 times 10 to the 23. And obviously going backwards the other way, you're starting with atoms and want to get all the way back down to grams. You need to use, once again, Avogadro's number to get you to moles. And once you're at moles, you can use the molar mass to go the rest of the way. So that is the relationship of how we can kind of put those 2 things together. Sometimes you may need to do that, may need to go all the way over. So there are problems, and definitely in this chapter and maybe in other situations, you may actually have to use the molar mass and Avogadro's number together. The key, though, as we mentioned a number of times at this point, you just want to make sure you don't overuse Avogadro's number in the wrong situation. We also could see the relationship, for example, of something that's not an element. So if I had 1 mole of water, we calculated earlier that water would be 18.01 grams. And that also would mean, though, if I had 1 mole of water, I would have 6.022 times 10 to the 23 molecules water. So once again, that is the relationship between those two. That's also why, for example, if you look at a mole of some of these substances, they may not look in terms of the same amount of something. So, for example, a mole of sulfur represents 3207 grams, while a mole of carbon represents only 12 grams. So you could have a mole, say, of sulfur, and maybe a mole of carbon, maybe a mole of sodium chloride, whatever it may be. And they may visually look like there's different amounts of it, but it can still represent 1 mole of something because, again, a mole of sulfur represents numerically a different number of grams than a mole of carbon. Or a mole of aluminum, as we see on this slide here, represents 26.98 grams of aluminum versus 12.01 grams of carbon for a mole. So those are very important sort of relationships that we see. All right, so let's take a look here. Why don't you take a moment here? How many moles of helium are there in 5.46 grams of helium? In case you don't have a periodic table, you might want to grab one, but we'll put it up here. You looked at the periodic table, looked up helium. That is what it will sort of look like there. It's a really bad 3. Give that a even worse sort of fix there. Try that one more time here. 3. There we go. All right, so take a moment or two and see what you come up with here. So here we want to know how many moles. We're starting with grams. So what we want to think about is we are going from grams to moles. Do I need Avogadro's number? I'm hoping at this point you are shaking your head no, hopefully. You do not need Avogadro's number here. There's no mention of atoms. There's no mention of molecules. Leave Avogadro's number out of this. What we do have, as we can see here, is a conversion between grams to moles. And as we know, our conversion to do that is the molar mass. And once again, we get the molar mass from the periodic table is where we get that. And that again is the number that we see right there on the bottom. And what that means is there are 4.003 grams of helium in every 1 mole of helium. Or really the molar mass of helium is 4.003 grams per mole. That means that we can write 2 conversion factors here that will be very helpful for us. We can write 4.003 grams of helium over 1 mole of helium, or 1 mole of helium over 4.003 grams of helium. Remember that we want to basically just do opposites here and set it up using dimensional analysis. So 5.46 grams of helium. Once again, grams are up on top, which means in order to get it to completely cancel correctly, we need to go opposites. So our grams need to go on the bottom. And we're going to do 4.003 grams of helium per mole of helium. Our grams are going to cancel. So once again, here we're going to multiply whatever's up on top, divide by what's on the bottom. In this case, it's really just 1 up there. So we're going to take 5.46. You don't really need to multiply it by 1. We're going to divide it by 4. You don't put 7 in your calculator. I'm going to try that again here. I guess 7 is like a 4 if you close your eyes. 5.46 divided by 4.003. That's going to give us on our calculator here like a 1.36 moles of helium. Really, on your calculator, you got something like 1.363977017. Significant figure wise, really an exact number, so do not need to worry about it. Coming back to our original number here, that is 3 significant figures, which is why we end up here at 3 significant figures. So hopefully you got that. And again, a reminder that you should be setting these things up like this. We're using dimensional analysis where you can see the units cancel, the conversion factors. It's really important that you do set up everything this way. All right, let's take a look at another one here. I think we've got a few more. What is the mass in grams of 1 AU atom? That is gold. And take a look at the periodic table here. Gold is 109.7, I believe. I'm sorry, 197. That is what I'm going to try to say there. So if we look up gold here on the periodic table, 197.0 is what you will see. All right, so why don't you give that a try? Take a minute or two and see what you end up with. We're looking for what is the mass here of one individual. All right, so let's take a look at it here. Hopefully you took care of it and got an answer. Reminder, make sure you are pausing and trying these things yourself first before you continue on with the video. So here we're looking for what is the mass in grams of 1 gold atom. So clearly here we have atoms, and we want to get all the way down to grams. So the key is, should I need to use Avogadro's number in this case? And the answer is, yeah, I do, because that's the key word there to tell me probably need to use Avogadro's number somewhere along the way. Remember that going from atoms to grams, or grams to atoms, or even molecules to grams, or grams to molecules, the thing that sort of ties us in the middle there is our friend, the mole. So the mole is sort of the middle unit that allows us to go all the way from sort of one extreme to the next. Remember that going from atoms to moles, that's going to be our Avogadro's number, and moles to grams is going to be our molar mass from the periodic table. So we do need a couple relationships to help us get to our final destination here. We need from the periodic table the molar mass of gold, which would be 197.0 grams per mole. And again, we get that from pulling this number off. By the way, on my periodic table, it's like 196.7 or 8 or something like that. So that's why we rounded up to 197 even. That gives us 2 conversion factors that we could use for the molar mass. We could say 197 grams of gold over a mole. We could also say a mole of gold is 197.0 grams. We also know that I do need to use Avogadro's number. So that means that if I had 1 mole of gold, that would equal my Avogadro's number, 6.022 times 10 to the 23. In this case, it would be atoms, since we're just talking about gold. That also gives me 2 conversion factors that I can use. We got 1 mole of gold is 6.022 times 10 to the 23 atoms. Or we could throw Avogadro's number up there on top, 6.022 times 10 to the 23 atoms is 1 mole. So we pretty much got everything here that we need to use. So let's set up this problem and get to our answer. So we're going to start with what was given to us, which is basically just 1 gold atom. So I'm going to use my Avogadro's number first here to do that. Doing it like we've talked about, opposites cancel. So I have 1 gold atom up on top, which means in order for it to properly cancel, I do need atoms on the bottom. So setting up dimensional analysis here, we're going to put our Avogadro's number actually on the bottom here, 6.022 times 10 to the 23 atoms of gold. Just kind of write it right there. and that equals 1 mole of gold. If I were to stop the calculation right at this point, the atoms of gold on top and bottom would cancel out. I would be left with moles of gold, which if that's what I'm looking for, I could just punch it into my calculator and pretty much be done with the calculation. Now, you could do that and you could get an answer at this point and then do the next conversion. Remember that if you do it sort of in parts like that, where maybe you get an answer at this point, you don't want to round too much here until the end. But if you want to continue on with the calculation, you could do that. And that's what I'm actually going to do here. So I'm not going to get a number at this point because I don't really need to know for this problem how many moles I got. But now I want to go from moles to grams, and I know molar mass is my way of doing it. Now, the benefit and the reason why you should set up your problems like we're doing here on the screen, which is using dimensional analysis and showing where the atoms are located, or the units are located really, we could clearly see that at this point, the units of moles are up on top. So that makes what conversion factor I should use really easy, because I need to go opposite. And the one that goes opposite is this one here. That put moles on the bottom. So remember, opposites cancel. And that's going to be my next part of the conversion, which is a mole of gold will go on the bottom. 197.0 grams will go up on top. Now the moles on top and the moles on the bottom will cancel. And at this point, I am left with units of grams. Why is this really important? Because people, when they do not set it up like this using dimensional analysis, they just kind of do the no units at all, or whatever it may be, stacking method, where they just kind of keep putting something divided by something. A lot of times what happens is people will frankly screw up. They'll screw up the calculation. They'll multiply when they should be dividing. They'll be dividing when they should be multiplying. They're not really sure like where the units are. But if you set it up like this with dimensional analysis, you can clearly see where the units are. Are they on top? Are they on the bottom? And that makes it a lot easier, that you're probably not going to mess up the calculation part, because once it's set up like this, what you know is pretty much what we've been talking about, that anything that is up on top gets multiplied, right? So anything that's up on top gets multiplied, then you hit equals, and then you go back and divide by whatever's on the bottom. And by the way, as we also talked about, I think in an earlier chapter, also don't be afraid to hit that equal sign in between dividing on the bottom, and obviously hit equals. So setting it up like this is both how you should show your work in chemistry. It also helps you in the math part of it, that you just also remember everything on top gets multiplied, anything on the bottom gets divided, and it helps you make sure that you are punching this in correctly. We also have Avogadro's number in here, which means we also want to make sure that we use our exponent button when we do this. So we're going to start here on top. On top, we really have 1 times 1, which if you want to put it in your calculator, you can, but you don't really need to. So we basically have up on top 197. We're going to divide it by Avogadro's number, which again, we want to make sure we use our exponent button, 6.022 exponent button 23, and hit equals. And that will get us a number like 3.271. Do not forget the exponent part on your calculator, times 10 to the minus 22 grams of gold. Now, what do I mean by don't forget the exponent part? So on my particular calculator, and your calculator might be a little bit different, but if I look at my calculator, it's displaying something like this. Let's see here, 3.271338843. I got an E and a minus 22. So very common mistake, people, when they see something like that, and yours may have an E in there, may have like a little times 10 part in there, in your display is what we're looking at here. So this is the actual display window of my calculator, what it looks like, and yours may look something similar. People oftentimes will forget this part of the number when they go to give the answer. They'll just give like the front part. So really important, don't forget that back part of it, and write it as a proper scientific notation. and we end up with this. That is a super small number. That's 22 places to the left and add zeros, which is what one individual gold atom is. You can physically pick up one gold atom and put it on a balance to weigh it. But here, using calculations, we get an idea of the mass of one individual gold atom. Now, you may be also wondering, why did I go to 4 significant figures in this particular case? So the answer is this. When we look back at our calculation here, where we got a lot of stuff there, so maybe I'll just kind of clean it up a little bit around there. Try not to miss everything. Yeah. Hey, I should get an award. I did that successfully. All right. So looking back at our calculation, really this conversion is sort of an exact number. So you don't really have to worry about it. This one's also an exact number. So really the only number we had to work with is basically this number right here, which is 1. It kind of comes back to what we were talking about, exact numbers. If you had something like 1 pen on your desk, once again, is probably something that you would count. You wouldn't figure out scientifically how to figure out how many pens you have. Same idea here. You pretty much can't pick out one gold atom by itself. But if you did, it would be really an exact number and something that you would count, which means it has unlimited number of significant figures, which means I just went with 4 significant figures based on the molar mass here. You really could have used any amount of significant figures in this case, because pretty much everything is an exact number, which has unlimited number of significant figures. All right, so that was a nice one. We did have to use both things together, Avogadro's number and molar mass. Let's keep going through some more of these examples here. And again, make sure you are working these out yourself. So we're going to look at our friend zinc here, and we want to know how many grams of zinc are there in 0.256 moles of zinc. And once again, if we go to the periodic table and find zinc, we're looking at 65.39 there. All right, so take a moment and see what you come up with. All right, so let's take a looky here. Once again, we really want to analyze what we're looking at here. So we're definitely looking for grams. So that's like where we want to end up, is grams. We are given, once again, MOL is moles, not molecules. So moles is what that is. So we have moles, and we basically want to get to grams. So the first big question of the day is this an Avogadro situation? And once again, I should hopefully be seeing, if I could see you should be shaking your head no. Again, there is no mention of atoms. There's no mention of molecules. We're going to leave our good friend Avogadro on the side there. We're not going to use it. This, again, is a basic conversion between moles and grams. And at this point, we should hopefully remember it is the periodic table and the molar mass. That is our conversion factor to do that. So we would obviously go to the periodic table. Wonderfully drawn here, sort of. And we can pull the number on the bottom, once again, to 4 significant figures. And we are looking at this, that it is the molar mass of zinc would be 65.39 grams per mole. That's going to give us our 2 conversion factors that we could use, 65.39 grams of zinc over a mole. Our mole of zinc is 65.39 grams zinc. By the way, side note here, which is also an important thing to remember, when you are asked to calculate molar mass of something or get the molar mass of something, you should only do it based on the formula. So, for example, I'll take a side trip here on this question. If we had something like water, right, and you wanted to calculate the molar mass like we were talking about previously, where we calculated it as 18.02 grams per mole, and that was based on the formula of 2 hydrogens and 1 oxygen from the periodic table. Now, let's just say in a chemical equation, you see water and you see a coefficient in front of it, like a 3. A very common mistake that people will make is when they go to calculate the molar mass of something like that, they'll try to incorporate the 3 into the molar mass. They'll times it by 3 or something like that. So it's really important, and we'll see some more examples of this in a later chapter as well. It's really important if you're asked to calculate the molar mass of something, you want to do it based off of just the formula by itself. If it happens to be in an equation, it happens to have a coefficient, you ignore the coefficient for molar mass. You just look at the actual chemical formula of it, and you calculate based off of that. And it's always per 1 mole, which is why we don't take into account the coefficient, for example, in an equation. So may not make 100% sense yet. We will see some examples where people sometimes will sort of calculate the molar mass incorrectly, especially when there's equations involved and there's coefficients in the equations. So the thing to keep in mind is molar mass of anything is simply based on if you took one of the formulas by itself and just go to the periodic table and calculate what it is. So back to the problem here that we're working on. We have given to us here the moles. So that is where we're going to start, 0.256 moles of zinc. Once again, we know that this is on top the moles, so we want to go opposites to cancel, and that's going to do it for us there. So we're going to put our 65.39 grams of zinc over a mole of zinc. Once again, the moles of zinc will cancel. In this case, we're just multiplying what's on the bottom. You also are dividing by multiplying what's on top and dividing by what's on the bottom. But really, in this case, it's 1 on the bottom. Although a lot of times people won't write it, it is a 1 on the bottom. So you really don't need to multiply it by it. So we're going to go 0.256 and we're going to multiply by 65.39. And that's going to give us a 16.7 grams of zinc. Once again, in terms of significant figures, we're not going to look at this as that's sort of an exact number. We are going to come back to this number and look at it, and that is 3 significant figures. And once again, that is where we ended up with our answer. On my calculator, again, 16.73984 is the number actually staring at us. Remember, we do want to kind of clean everything up to the proper number of significant figures. So once again here, no need for Avogadro's number as there's no molecules or atoms in this problem. We also want to make sure that when we calculate molar mass, as we just talked about, always based on just taking one of the formulas by itself and adding up the parts on the periodic table. All right, let's take a look at a couple more here. We have 2 problems here, kind of based off of the same formula. And in the first one, we're looking for how many moles are there in 23.2 grams of ethanol, which is C2H6O. And we're also looking for how many molecules there would be in that 23.2 grams of ethanol. Let me give you some information. If you don't have a periodic table with you, which might be helpful, our good friend carbon is 12.01. Our friend hydrogen, 1.008. And our good friend oxygen is 16. 16, there we go. All right, so we're actually looking for 2 answers. We're looking for how many moles, starting with 23.2 grams of ethanol, and how many molecules. So take a few moments here and calculate both of them, and then we will go through it. Okay, let's take a look and see. Hopefully you've got both answers. Once again, make sure you do before you continue on watching the rest of this. We are looking at the first one there. We are starting with grams and we want to end up at moles here. So once again, from our conversations, we should know that's going to be our molar mass that's going to get us there. The second one, we actually want to end up in molecules. And we know that the moles is really the kind of middle road there to end up at molecules. And that is the key word that tells us our friend Mr. Avogadro's number needs to be used here. So really, these both go together. We just need an answer on both of the steps here. And we're going to use molar mass to go from grams to moles and moles to molecules using Avogadro's number as sort of our pathway here. So we do need to get a few pieces of information here. Clearly, we know that there are 6.022 times 10 to the 23. Here we're going to use molecules, as ethanol is a molecule. And a mole of ethanol, C2H6O. Or we could use it in the opposite way, that a mole of ethanol, C2H6O, is, do my best to squeeze this in here, 6.022 times 10 to the 23. I'm just going to write molecules underneath it. Maybe put a C in there would be good. There we go. So these are our two conversion factors for Avogadro's number, which we need really for this part of it and the second part of the question. We also need the molar mass. Now, this is a molecule in a compound. So remember that when we have something that is a compound or a molecule, we basically just go to the periodic table and we use the numbers that are on the bottom, which are the molar masses. And essentially what we do is add up all the parts. So let's do that. So there are 2 carbons. So each carbon from the periodic table is 12.01 grams per mole. We're going to add that to our hydrogens, and there's 6 of them. And that is this number right here, right? And again, it always goes to the guy to the left. And it's going to get us 6 times 1.008 grams per mole. We're then going to add it to our hydrogen. Remember, if there's nothing written, that's assumed to be 1. So we would have 1 oxygen at 16 grams per mole. This represents, once again, our carbons. That is our hydrogens. And this represents our oxygens. So we're going to add all that together. And we'll go right about here. So we're going to take 2 times 12.01. We're going to add it to 6 times 0.008. Going to add us a lucky 16 there. We can go 4607. Once again, that number is 46.07 grams per mole. And that is the molar mass of our ethanol. That is also can be used as a conversion factor. So once again, we could use that as 4607 grams per mole. Or we could flip it around and do a mole of ethanol is 46.07 grams. So remember, from the molar mass, we could get 2 conversion factors that we could use. Not going to use them both. Going to use the one that is opposite of where we're starting. So now that we got everything that we need, let's do the actual problem. We'll start with the first one, which is 23.2 grams of ethanol. Once again, setting up dimensional analysis way, we see grams of ethanol are up on top, which means molar mass wise, we need to use the one where the grams are on the bottom so that everything cancels out correctly. So that's going to be 46.07 grams per mole ethanol. And the grams are going to cancel out. Now, because we are looking for an answer here, we're not going all the way to molecules. We are eventually, but we actually do want how many moles there are. We're going to actually get the answer here by taking 23.2, dividing it by 4607. And in this case, I'm going to actually round to proper sig figs, which would be 3 based off of our first number here, this exact number. Don't have to worry about it. So on my calculator, I can get 0.504 moles of ethanol. So that is our first answer. Now, on my calculator, I got 0.503581506. It's important to remember that in this case, we do want to give our answer to proper number sig figs for our first question, but we're really going to be continuing on and using that number in the next calculation, which is down here. So for me personally, what I would be doing at this point is pretty much what I'm going to do. I'm just going to use the entire number I have in my calculator, so the non-rounded version. If you want, as you continue on with your calculation for the next question, you may want to take it to a couple extra digits, or you could just keep the number in your calculator and use them all. Again, you don't want to round too much. I don't think it'll be a tremendous difference in this case, but sometimes it can be. So to recap what I'm just talking about, I am going to round correctly here. So I get the answer for my first question. I'm going to actually continue on with that number because that's what I need to do the next part of the calculation. But although I am writing the rounded number here on the screen and on my paper, I am going to use on my calculator here the whole number that I got, so in the non-rounded version. So again, just so we don't get any type of rounding sort of errors or situation, again, you want to take it maybe to a couple extra digits or keep all the digits and just continue on with the calculation. All right, so continuing on with the calculation here to wrap up this one, we can see now we have moles up on top. So going to our Avogadro's relationship, we need moles on the bottom. And that is the guy here on the left that we're going to use. And that means that we will have 6.022 times 10 to the 23. And again, these would be molecules of ethanol over a mole of ethanol. And once again, the moles here will cancel. Using my non-rounded number, I'm going to multiply it by Avogadro's number. On the bottom is really 1, so you don't really need to divide by it. And if I do that, and again, making sure I use my exponent button correctly, we will end up with here 3.03 times 10 to the 23. And these would be molecules of our ethanol in this case. So this is really sort of like this second calculation or so that we did there. We're going all the way to molecules, but we are stopping along the way here for moles. So again, I did a little bit more rounding on the first part because we were looking for an answer. But again, continuing on to this part of the calculation, I use the unrounded number in my calculator and continuing on. So hopefully that makes a little bit of sense. It may not, again, make a tremendous difference here in this particular case. So just to see if it did, if I used a rounded number in this particular case, which is 0.504, and times it by Avogadro's number, we actually will end up with 3.04, for example, on the rounding, times 10 to the 23. So if your next question is, and I can maybe hear it right now, what happens I did use a rounded number and I wrote 3.04 times 10 to the 23, are you going to mark it completely wrong? The answer is yes. No, I'm just kidding. I'm not going to mark it wrong. It will be probably okay. But again, just so you know, try not to round too much, especially if you see yourself going on to a further calculation. And again, try not to round to the very end. But in this case, we did need to do a little bit of rounding there because we were given an answer. So you ended up with 3.04. By the way, on my calculator, I ended up with 3.035 times 10 to the 23 when I used a rounded number, which would round up to 3.04 times 10 to 23. In this case, you would be okay in this situation. But I try to avoid those issues. Definitely try not to use too much of the rounded number unless you're completely done with the calculation. Hopefully that makes sense. Also, a couple of things that you might be also thinking about, like, what do I need to show? So truthfully, on an exam or something like that, you should show, some calculations here of molar masses. You should show the setup here with the proper units. That is definitely what you should show to receive full credit. If it helps you to write out all the conversion factors, like we were doing, like, maybe go back to a pen here. Like we were doing over here, or even over here. If it helps you to do that, or this part, you could definitely do that. But for full credit, you minimally need to show the dimensional analysis sort of setup, all this stuff. And if it's anything that you need to calculate molar mass, you need to show your calculation of molar mass. You don't have to do the conversion factors or all the conversion factors. But again, if it does help you, definitely do it. All right, let's take a look at another one here. I think, what is the mass in grams of 1 molecule of caffeine? Maybe you're drinking some of that right now. There's the formula. That's a big formula there. That's 8 carbons, 10 hydrogens, 4 nitrogens and oxygen. So once again, in case you maybe don't have the periodic table with you, if you look at the periodic table, as we saw in the previous problem, 12.01 for carbon, hydrogen 1.008, nitrogen 1401, and oxygen 16. All right. So in this case, we're looking for what is the mass in grams of one molecule of caffeine. So take a few moments and see what you come up with here. All righty, let's take a look, see how you're doing. So once again, you do want to sort of analyze these things, make sure you understand maybe your pathway of where you need to go, where you're starting. Sometimes really helpful than just jumping right in. Right? It's always good sometimes to look at directions before you go somewhere. Maybe not as fun sometimes, but always good to know sort of where you want to end up. So in this case, we want to end up in grams, as we can see from the problem. We have molecules given to us. Once again, as we've seen in a number of problems, the one that sort of ties these guys together is our friend mole. So that is sort of our pathway where we need to go. A reminder, molecules, also the key word, that is how we get to moles. Avogadro's number does need to be used here. Going from moles to grams, that once again is our periodic table and our molar mass here. So right off the bat, we know Avogadro's number, one molecule in this case. I'm sorry, no, let's try that again. Get that eraser out there. All right, let's try that here. Grab that, there we go. We know that in 1 mole of caffeine, that's what I was trying to say, there are 6.022 times 10 to the 23 molecules of caffeine. That obviously gives us our 2 conversion factors, very similar to what we've used previously. 1 mole caffeine over 6.022 times 10 to 23 molecules are 6.022 times 10 to 23 molecules over a mole caffeine. We also will need our molar mass, which always comes from the periodic table here. Just like we did previously there, we're going to add up all the parts. So here we go. We have 8 carbons. So we're going to take 8 times our 12.01 grams per mole, which is our molar mass of carbon from the periodic table. We're going to add that to 10 hydrogens times 1.008 grams per mole from periodic table. We have 4 nitrogens, so plus 4 times 14.01 grams per mole. Obviously from our periodic table, and 2 times our oxygen, so 2 times 16 grams per mole from our periodic table here. Adding all that together, going to be 8 times 12.01 plus 10 times 1.008 plus 4 times 14.01 plus 2 times 16. Looks like 194.2 grams per mole. All right, so we got everything we need. Again, we could use this as a conversion factor, either grams over moles, or we could flip it in moles over grams. Remember, the number stays with the grams. We're going to start with our 1 molecule of C8H10N4O2. We're going to use our Avogadro's number. So we want molecules on the bottom. So we need to put this on the bottom. So that would be 6.022 times 10 to the 23 molecules over 1 mole of our caffeine. Again, if I stop right at this point, molecules will cancel. That brings me to right there. So now I need to go the rest of the way. Once again, you can get an answer at this point, or you can continue on with the calculation. And that's what I'm going to do. I'm going to continue on with the calculation. I could clearly see from my writing here that the moles of caffeine are up on top, which means I need to put the moles of caffeine on the bottom using our molar mass. So a mole of caffeine will equal 194.2 grams. Moles will cancel. Again, we're going to multiply what's on top and come back and divide by what's on the bottom here. So basically we have just 194.2 on top divided by 6.022 to the 23, making sure to use our exponent button. And at this point, we will end up with 3.225 times 10 to the minus 22 grams of caffeine here. Big formula. Once again, this is a similar thing that we saw before, kind of an exact number, really an exact number. So once again, I took it to 4 significant figures, really based on the molar mass. You could actually take it to as many as you want in this case, since they're all really sort of considered exact numbers. So hopefully that is what you got. Make sure you're using that exponent button. Let's take a look at one last thing here in terms of molar mass, Avogadro's number, and calculating certain things from formulas. So sometimes we are maybe not asked about the entire compound. Maybe we're asked about a particular part of the compound, how many moles, how many grams, how many atoms there are. So for example, we'll take one like we were looking at previously. We'll take our ethanol, I think. Let's take our ethanol here. So let's say we had our 23.2 grams of our ethanol. And let's say in this case, we wanted to know how many moles of hydrogen there are and how many atoms of hydrogen are there. So we want to approach this problem a little bit different. And the difference in this problem is we are starting with ethanol here, which is all three of those elements, carbon, hydrogen, oxygen together. We're actually just interested in the hydrogen part. So in this situation, we need really a conversion factor that allows us to go from the whole thing to just the one element that we're interested in, which is hydrogen. And where can we get that conversion factor? We actually can get it from the formula itself. When we look at these bottom numbers, these subscripts, these actually represent, and again, obviously nothing's written there which represents one. These actually represent the moles of each of these elements. So we could actually write several relationships from the actual equation itself that will allow us to do this calculation. For example, we could say in 1 mole of the entire thing, there is 2 moles of carbon. And that 2 basically comes right from there. We could also say in 1 mole of the entire thing, there are 6 moles of hydrogen. And we could say in 1 mole of the entire thing, there are 1 mole of oxygen. Once again, if nothing's written there, it represents 1. These are actually equalities, which means for each of these, we could write 2 conversion factors. So I'm going to look at just hydrogen since that's what we're looking at. So we could write in 1 mole of the entire thing. That gives me 6 moles of hydrogen. Or I could write in 6 moles of hydrogen. There's 1 mole of the entire thing. So this is actually the conversion factor is going to allow us to go from the entire thing to just that one element. And we could actually use the formula to do that. So let's do that here. We're going to first need to convert the entire thing into moles, because that's the only way this kind of mole to mole relationship is going to work. So I'm going to cheat a little bit since we used this previously. And previously we saw that the molar mass here of ethanol was 4607. So I'm going to just use that number. And obviously we calculated that the exact same way as we did on that previous example. And that would be coming from the periodic table, adding up all the parts, the 2 carbons, the 6 hydrogens, and the 1 oxygen. So I'm going to take our original number here, 23.2 grams of ethanol, and I'm going to convert them into moles. And again, the reason I need to do that is so I could use this conversion factor, so all the units cancel correctly. Grams are up on top, which means I want grams on the bottom here. Grams will cancel. And if I stop right at this point and actually got an answer, I would be in moles of ethanol. I'm not going to do that because I'm actually looking for moles of hydrogen. So now I could go to the formula and use that conversion, which gave us these two conversion factors. And once again, setting it up like this, I can see moles of the entire thing's up on top, which means to get rid of it, I need moles of the entire thing on the bottom, which would be this version. So 6 moles of hydrogen gives me 1 mole of the entire thing. So here I'm using the formula as a conversion factor. That is actually going to get rid of the entire thing. And now I've went from the entire thing, in this case of ethanol, to just the hydrogen using the formula as a conversion factor. So I'm going to get an answer here because that's one of the questions I was looking for. So I'm going to take 23.2 times 6 and divided by 4607. And once again, I'm multiplying up on top and dividing by the bottom here. And that gives me 3.021. We'll go 5 moles of hydrogen. I'm going to clean it up here to 3 significant figures based off of that, which will give me 3.02 moles of hydrogen. So by using the formula here, I was able to convert from the entire thing to just moles of hydrogen, and that gave me this. Now I want atoms of hydrogen. So what is my conversion to go to atoms of hydrogen? That's the key word, is atoms. So just like before, now I can use Avogadro's number. So to use Avogadro's number here, I'm going to take the number I just got, which was 3.0215. I'm going to take a few digits out for this. Again, not using the rounded version. And I'm going to use Avogadro's number here. Moles are up on top, which means moles of hydrogen will be on the bottom. 6.022 times 10 to the 23. And these would be atoms of hydrogen, as we're dealing with atoms. Moles will cancel. That's our Avogadro's number. So we're going to catch my calculator and hopefully it doesn't fall off. And look at what number I'm looking at there. We're going to times that by 6.022 to the 23. Once again, I'm not using the rounded number here. And I'm going to end up here now cleaning up to 1.82 times 10 to the 24 atoms of hydrogen. So this is a problem. It's really the same steps as we did previously, but sometimes you are interested in maybe just one element in a compound or molecule or formula. You can actually use the formula as a conversion factor. So I just did one. Let me just make up one here. Why don't you give it a try just to make sure? Let's say we had 2.8 times 10 to the 14 molecules of methane. How many moles of hydrogen and grams of hydrogen is that? I will do it as well since I just made it up. Carbon, once again, 12.01. In the periodic table, hydrogen 1.008. All right, so take a few moments and find those two answers and see what you come up with. Hopefully not too bad. 50-50 shot when you make up a number. We'll hope for the best. All right, give it a go, and we'll talk about it here in a second. Okay, let's take a look, see how you're doing. So hopefully, again, we got a couple of things. We got molecules, and we want to get to moles, and we also want to get to grams. So that's going to be some molar mass action. That's also going to be some Avogadro's number. But before we could do all that, we might have to do some conversions here to see. We want to, though, get to moles of just the hydrogen in this case and grams of the hydrogen. So we do need to use the formula here as a conversion factor. So once again, those bottom numbers represent the moles. So nothing written there is 1 mole, and that is a mole. So we could say in 1 mole of the entire thing, there is 1 mole of carbon. And in 1 mole of the entire thing, there is 4 moles of hydrogen. And once again, that comes from here. And obviously, that came from there. So that's going to allow us to go from the whole thing to just hydrogen, which is what we're interested in. Now, in order to do this, we need moles of everything, but we are starting with molecules. So we will need to use Avogadro's number to convert from molecules of CH4 to moles of CH4, because then that will allow us to use this conversion. So that's where we want to start, 2.8 times 10 to the 14 molecules of CH4. We're going to use Avogadro's number again. It's going to go on the bottom here, so molecules cancel. And once again, at this point, if I stop the calculation right at this point, I am in units of moles of CH4, which is close to where I want to get to, but I do want to now get to hydrogen by itself. So this is where our formula itself and the conversion factor that we could get will come into play. And the reason I again needed to do this first conversion is to get it into moles of CH4 so that they will cancel. If you did not do that, the units will not cancel correctly. So now we want to get rid of the moles of CH4, and we want to end up with moles of hydrogen in this case, which is 4. Those will cancel. So again, here I'm going to get an answer because I am actually looking for that as one of my answers. So it's going to be 2.8 to the 14. Again, making sure you use the exponent button. We're going to multiply it by 4 and hit equals. So that's everything up on top here. We're going to multiply. And again, make sure you hit equals. We're now going to come back and divide here using our exponent button. And in this case, we're going to divide by 6.022 to the 23. We're going to hit equals. And in this case, we will end up with 1.9 times 10 to the minus 9. And these would be moles of hydrogen. Now, just so you know, I happen to have my calculator on scientific notation. If you did not have it on scientific notation, what you might see on your calculator is not the correct number of zeros, but a bunch of zeros and like a 2 at the end. A lot more zeros than what I wrote there. But and that's only because it's your calculator ran out of digits, so it just puts it all at the end there and rounds up. And if you had it in scientific notation, you'll get something like 1.859 times 10 to the minus 9. But if you did get this on your calculator, and again, there would be a lot more zeros there, and you're just kind of ended there with just a 2 at the end with all those zeros, it's just not in scientific notation, which is okay. You could record all those zeros or write it as 2.0 times 10 to the minus 9 probably, and it would be okay in terms of your calculation. So if you happen not to get this number in your calculator but got more of this thing with a bunch of zeros and a 2 at the end, that's what happened. Pretty much ran out of room on your calculator. So that sometimes happens. And it's okay to continue on with that number. You probably would want to put it in scientific notation, like a 2.0 times 10 to the minus 9, to make it a little bit easier to work with so you don't have all those zeros. Now, we also want grams now of hydrogen. So what we have is moles of hydrogen. So we could go to grams of hydrogen by using the molar mass. Now, it's really important at this point to remember that we're no longer dealing with CH4. We are only dealing with hydrogen at this point. So we want to use just the molar mass of hydrogen. So we'll continue on here with 1.9 times 10 to the minus 9 moles of hydrogen. Using the molar mass from the periodic table of hydrogen, 1.008 grams of hydrogen per mole of hydrogen. Moles will cancel, and we'll times this by 1.008, and that ends up at 1.9 times 10 to the minus 9, basically. grams of hydrogen. So again, here we could use the formula as a conversion factor. Although we did hydrogen in each of these examples, you could do this for either one. So just to finish it out, let's just say we had C2H4. And let's just say we had, make up a number here, 10.5 grams of it. And we want to know how many moles, we'll just do a short one here, of carbon that would be. So once again, we can use this formula here to get us our conversion factors to get to just carbon. 1 mole of the entire thing would give us 2 moles of carbon, and 1 mole of the entire thing will give us 4 moles of hydrogen. In this case, we're looking at carbon. So we're going to use that. Once again, we can't use it like it is because they're moles and we have grams. So we do have to convert grams of the entire thing into moles. So we'll go to the periodic table and 2 carbons, each at 12.01 carbons. We'll add it to 4 hydrogens from the periodic table. And again, we're getting from that bottom number like we've been doing. And we'll add that together, and that will get us 2 times 12.01 plus 4 times 1.008. Going to give us 2805. Is our molar mass for C2H4. So taking our 10.5 grams of C2H4, using the molar mass as a conversion factor, grams on top. So we want grams on the bottom here to cancel. Grams of the entire thing will cancel. Now that I have it into moles of the entire thing, this is where we could use our conversion factor from the formula. You could get an answer, but I'm just going to continue on with the calculation here. I got moles of the entire thing on the top, which means I need to go with 1 mole of the entire thing on the bottom. Gives us 2 moles of carbon. And again, we're going to multiply on top here. So that's going to be 10.5 times 2 divided by 28.05. Going to give us here 0. Whoops. Sorry, try it again. It's going to give us 0.749 moles of carbon. Now, we didn't ask for it in this case, but if I wanted grams of carbon, I could get the molar mass of carbon from the periodic table, which would be 12.01 grams per mole. If I wanted atoms of, not molecules, but atoms of carbon, I can use Avogadro's number at this point to 6.022 times 10 to the 23. So at this point, I could go either way. I could also obviously do the same calculation for hydrogen as well. So this is just a little wrinkle on some calculations for grams, moles, molecules, Avogadro's number. So sometimes you will come across a situation where maybe you're interested in just one of the elements in a formula rather than the entire thing. So using the formula as a conversion factor, where the bottom numbers represent moles, is really important. As we'll talk about in the next part of this chapter, knowing that those are moles is also important for empirical formulas and molecular formulas that we will talk about as well. But with that being said, I think that's probably a nice little start here to chapter 7, I think it is. So we will stop here for now. It looks like we will go on to probably a second lecture here for chapter 7, and we'll cover up the rest of the chapter, which is empirical formulas, molecular formulas, how to calculate them. I think this is enough to digest from the first part here, chapter 7. So with that, we'll stop. Have a good day or evening whenever you're watching on it, and we'll see you in part 2 coming up on the next lecture. Have a good one. Bye-bye. Hello there, and I hope you've enjoyed this lecture. I heard a funny joke the other day. It was so damn funny that I slapped my knee on that one.